First of all, thank you to the organizers for inviting me here. Okay, this talk will be based on joint works with Guido De Filippis, Fonseca, Nicola Fusco, and Giovanni Leoni. I will be dealing with the classical capillarity energy, so let me just start by recalling some classic facts about it. I'd like to start with a quotation from the famous book by Fins on capillarity surfaces. According to Fins, capillarity phenomena are all about us. They are, for instance, we see them, for instance, they are present in determining the shape of a drop of water on a leaf. We see them when they lead the rise of a liquid in a narrow tube, and many phenomena can be somehow related to the capillarity energy. And let's say that a capillarity phenomenon occurs whenever two fluids are put adjacent to each other and something happens at the interfaces between them. Usually these are two fluids, but in many physical systems there is also the interface can occur also between a fluid and a rigid solid, and often the presence of a rigid solid yields a dominant effect on determining the final configuration. Okay, these are examples of capillarity phenomena. As I said before, the rise of a liquid in a narrow tube, the sessile drop, or which is an idealization of the phenomena I was saying before. For instance, you can think of a liquid drop sitting on a leaf, a pendant drop, and for the purpose of my talk, also the growth of nanowires we will see has something to do with capillarity, and this will be actually the focus of my talk. Okay, the study of capillarity goes back even to Leonardo, and but the modeling, the mathematical modeling was started by Young and Laplace themselves, and then it was somehow put in a unified formulation, which is actually the modern formulation, the modern variational formulation, was found by Gauss. And how Gauss introduced the energy that we will be still using in our variational approach. The Gauss variational approach is based on the following simple physical phenomenon, which is the following, which can be described as follows. So between suppose that you have a liquid surrounded by a gas, and okay, there are forces acting between the molecules of the liquid and forces acting between the molecules of the liquid and the gas. The cohesive forces between the liquid molecules are stronger than those acting between the gas and the air. Therefore, if you take a molecule inside a liquid, this is equally pulled in all directions with a resulting zero net force, while molecules sitting at the interface somehow are drawn towards the interior because of the imbalance between the forces between liquid and gas, and this creates a sort of pressures forcing the surface of the liquid to contract to a minimal area configuration. So in the end, the basic principle is minimization of interfacial area. Based on this intuition, Gauss introduced the following variational formulation of the problem. And his idea was to associate to a configuration like this. So you have a drop here sitting on a rigid solid, and then surrounded by, say, air or by a vapor phase. And to any such configuration, the idea is to assign an energy which is the sum consisting in penalizing all the interfaces between the solid and the vapor, the liquid and the vapor, and the solid and the liquid. And all these interfaces are penalized, the area of those interfaces are penalized. So here in the rest of my talk, sigma will stand for the surface area, so the two-dimensional Hausdorff measure. And okay, so you penalize each of the interfaces between the three phases with weights. And these weights are the surface tension coefficients. Okay, there is a more convenient way of rewriting this energy by adding a constant term. So by adding this term, the area of this region times the coefficient, the surface tension between solid and vapor. By adding and subtracting this term, you can, this blue term here, which is a constant one, pops up. And therefore, as far as minimization is concerned, we can drop it. We can further simplify by we can normalize by dividing by this coefficient. So the energy looks like this. Since this is a constant term, and since we are interested in minimizing this energy, we can drop it out. And then as it is done usually, we are assuming the so-called wetting condition, which reads like this. Under this wetting condition, we can give a name to this coefficient. We call it, this is standard in the physical literature, it is called minus lambda. And so in the end, we can rewrite the total energy in this way. So this is the surface energy of the free boundary here, of this part of the boundary, minus lambda times the area of the wetting region, of the wet region, of this part of the boundary. And this will be referred to as the wetting energy, and lambda will be the wetting coefficient, which is something with modulus strictly less than 1. Okay, in the Gauss variational approach, the configurations, the observed configuration are minimizers or local minimizers of the energy under a volume constraint. Okay. You can possibly add to this energy a potential energy, potential term, so a volume term, accounting for the possible presence of external fields, like, for instance, gravity. But let me say that at least when in the small mass regime, this is a sort of lower order term. So this can be neglected. In the small mass regime, surface area somehow is dominant, and we can neglect volume terms. So as I said, equilibrium configurations are local or global minimizers of this capillarity energy under a volume constraint. Sometimes the volume constraint is replaced by a volume penalization. Okay. Once you have this variational principle by standard first variation argument, one can derive, and that's what Gauss already did, the so-called equilibrium conditions. So let me just quickly recall the result. If you start by varying, assume that E is a minimizing configuration. And now if you consider variations of normal variation of the boundary, which are compact, which are supported away from the contact line, so you are not moving the wet region, the wetting region, and then you differentiate the energy with respect to these variations, you find out that the criticality condition is given by this expression. In particular, the mean curvature of this part of the boundary pops up, and G is the possible presence of the external field. And so the stationarity condition becomes that this quantity must be constant on this part of the boundary. So the mean curvature plus the potential term has to be, the sum of these two terms has to be constant. Particularly if there is no potential term, the mean curvature has to be constant. So capillarity energy in the absence of gravity are constant mean curvature surfaces. But this condition, this stationarity condition, must be supplemented with the so-called contact angle condition, which is given by the Young's law. And which is telling us that the minimizing configuration meets the rigid support, the solid support, with a contact angle, this one, which is prescribed by the following law. So the cosine of this angle, which will be referred as the Young's angle, theta y, must equal the wetting coefficient, so the coefficient appearing here in the wetting energy. And again, this is obtained once again by a first variation argument, now by considering variations that also move the contact line. Okay, this is a standard calculation. Okay, the effect of the Young's law is well described by the sessile drop problem. So now let us consider the following problem, which is also very classical. We want to minimize the capillarity energy in the Hall space. So the support, if you want, the rigid solid is the lower Hall space, and you want to minimize among all configurations lying above is a flat plane with prescribed volume. We are neglecting gravity, so we assume that G is equal to 0. So we are in the small mass regime. And in this case, the solution is well known, and it is given by, for every lambda, the global minimizer of the capillarity energy in the Hall space is a spherical cap. Which spherical cap? The one which meets the boundary with the right contact angle, with the contact angle given by the Young's law. And of course, satisfying the volume constraint. This is very classical, can be proved by symmetrization arguments. So you see in particular when lambda is negative, minus lambda term is positive, so you're penalizing a lot the wetting region, therefore you want to somehow you want to decrease the wet region, while when lambda is positive, it is convenient for you to increase the wet region, that's why you get this smaller angle. In the lambda equal to 0 case, where you only see this the relative perimeter of the drop, you have this you have the contact angle is pi over 2. So this part of the boundary meets the half plane orthogonally. Okay, so now let me come to the nanowire growth model. And well, first of all, let me recall what nanowires are. Nanowires are essentially one-dimensional structures, so very thin and long structures with a cross-section much smaller with respect to the length. So that approximately we can consider them as one-dimensional. They have a lot of technological applications, for instance, as in nanoelectronic devices. They can also be used as battery electrodes, and they also find applications in biological applications. For instance, since they are very thin, they can be used to penetrate biological membranes without damaging them. A typical process to grow a nanowire is by the so-called solid vapor liquid method, which consists in the following. So a liquid drop of catalyst here sitting on the upper face of the wire facilitates the absorption of atoms from the vapor phase, from the surrounding vapor phase, and so this liquid drop absorbs atoms from the vapor, and then up to some saturation levels, and then leaves some nucleated seeds at the interface with the solid, feeding then the vertical growth of the nanowire. And how capillarity comes into play? Well, in determining the shape the behavior of this liquid drop here. Okay. So we are essentially following the physical literature. We model the nanowire as a semi-infinite cylinder, like here in A, with a cross section given by any convex bounded domain in the plane, or like a truncated cone, again with the same cross section. The cross section omega here. Okay, in this drawing is circular, but it can be any convex domains any convex bounded domain in the plane. And since we are in the small mass regime, we can neglect gravity, and therefore the minimizing the configurations, the shape of the drop here is described as a minimizer or local minimizer of the pure geometric capillarity energy, which again is the one that I've written before. So we penalize the area of the part of the boundary of the drop outside the Y, and then there is this wetting energy. And we want to minimize this energy under the volume constraint. So mathematically, the first question that one asks is whether there are globally minimizing configurations. So this is the first question that we addressed. The paper with Fonseca, Fusco, and Leoni. And well, the answer is that yes, in general, for this situation here, for the cylinder, for the semi-infinite cylinder, there is always a global minimizer of this energy under volume constraint for any lambda, between -1 and 1. While in general, one cannot expect the existence of global minimizer for this situation, for the situation of the cone, of the truncated cone. And well, at least in the case when lambda is equal to 0, so you just have the relative perimeter here and not the wetting energy, we were able to prove that in general you don't have a global minimizer provided that M is sufficiently large. It is provided that you don't have enough space to accommodate a half sphere on the top of the wire. And the reason why, well, let me comment on these non-existence results. This is related to the fact that, well, this is the following isoperimetric inequality outside convex sets, which says the following. So I stated this isoperimetric inequality in 3 dimensions, but in fact it is true in all dimensions. This is due to Choi, Gomi, and Ritoré, and also with Nicola, Fusco, and myself, we settled the case of equality. But so this inequality says the following: that if you have S is any closed convex body, then for any configuration, like here, lying in the complement of this convex body, the relative perimeter of such a configuration, that is the area of the part of the boundary which is not lying on S, is larger or equal than the corresponding the relative perimeter of a Hall sphere lying on a Hall space and having the same volume. With inequality being strict unless E is in fact a Hall sphere lying on a flat facet of the convex body. If the convex body doesn't have any flat part, the inequality will always be strict.
And quick question, and if it's strictly a cone, then you don't have minimizers ever.
If it is a cone,
yeah.
In this case, no, we don't. For the same reason, we don't.
Same reason. And this wasn't known?
Sorry?
This wasn't known?
No, I don't know.
Remarkable.
Okay, in this, for this particular problem, probably. I'm not claiming that this is surprising, but it's just, if you want, this is just an observation, yeah. So the idea, so you probably already know how it goes. So the idea, why do you have a non-existence? Because, okay, you can, the point is that you can slide down, I mean, minimizing sequence can escape to minus infinity, and here, in fact, it is convenient to take a minimizing, to consider a configuration which slides toward minus infinity. So because of the isoperimetric inequality that I stated before, you have, for any admissible configuration, you have strict inequality. You have this strict inequality, so the energy of any admissible configuration is strictly larger than the one of the corresponding Hall sphere. On the other hand, you can take essentially quasi-Hall spheres, so by intersecting your by taking a sphere and intersecting with the truncated cone and slide this configuration towards minus infinity. Since towards minus infinity, the surface, the boundary of the cone becomes flatter and flatter, in the end you are converging to a Hall sphere, and therefore you are approaching the infimum of the energy. So in this case you have no minimizers. Probably this will be true also for lambda different from 0, but what is missing is the corresponding isoperimetric inequality. Okay, how do you prove instead the existence for this configuration? Well, one way is the following. So what the approach that we followed is the following. We start so we consider a sequence of balls with diverging radii, and so the idea is to start by minimizing under the additional constraint that your sets must be confined inside this diverging sequence of balls. So, and another technical fact, it is convenient to replace the volume constraint by a volume penalization. So this is a lambda, a large lambda, which penalizes the volume. So instead of imposing an exact volume constraint, you penalize it. Well, and then for lambda, for any n, by standard methods, one find a minimizer of the capillarity energy plus this volume penalization under the constraint that everything must be confined inside this ball. Then some volume density estimates, some regularity arguments, namely by providing volume density estimates, which is also rather standard in this type of arguments. One can show that for any lambda, for any n, the minimizer of this problem has a finite number of connected components, and a finite number, a number of connected components which is bounded by a quantity which only depends on lambda, but not on n, and also the diameter of such connected components is bounded by a constant which only depends on lambda. And okay, and this then we have this essentially uniform bounds on the diameter of the conotic component. Because of course, now we are considering the vertical cylinder. If we have a connected component lying on the vertical part of the boundary, you can slide it upwards without changing the energy. So by sliding up this, if needed, the connected component of the minimizer, we may enforce, and using these uniform bounds on the number of connected components and on the diameter of the connected components, we may in fact enforce that the minimizing sequences are equibounded in a way that independently of n, and therefore by letting n to plus infinity up to a subsequence, we may assume that such a minimizing sequence converges to a set which in the end will be a minimizer of this functional without now this constraint. Okay, then the last part of the argument is to show that by choosing lambda sufficiently large, in fact, the volume constraint is actually attained. Okay. Okay, next we were interested in studying the so-called edge pinning effect. Let me illustrate with this picture what we mean by that. It's something which is observed in the experiments. So you start first, consider this configuration. You have a drop, a little drop, which is completely contained, which is well contained in the upper face of the wire. Well, what is the shape of such a drop, minimizing drop? Well, it's a spherical type. This is like the sessile drop that I said before. It's a spherical cap meeting the flat surface with the Young's angle. Then you start growing this drop until it touches for the first time, until the contact line touches for the first time the edge of this upper face. Again, at this point, the angle is still the Young's angle. But now at this point, if you increase a little bit more the volume of the drop, what happens is that there is no immediate spillover of the drop on the lateral boundary, but instead the drop remains pinned on the upper part of if you want, the contact line remains pinned at the edge of the face of the wire for a while. So there are configurations where in fact the contact angle is larger than the Young's angle. Okay, so what we wanted to do in this very simplified geometric situation, now here I'm assuming that the section is circle, so we are considering symmetric nanowires, and therefore here we have really a spherical cap. So we want to understand for which range of angles, theta, larger than the Young's angle, this configuration is a locally minimizing configuration. Okay, and this is what we found in the same paper with Irene, Nicola, and Giovanni. We have this characterization. The range is this one. So for angles which are simply larger than the Young's angle and below this threshold here, and I will comment on this threshold, then the spherical cap here is in fact a local minimizer, a volume constrained local minimizer of the energy. While as soon as you increase, once you reach this critical angle, if you increase further the volume, and so if you increase the angle, then there is spillover. And it is convenient for the drop to spill over the lateral boundary. And so, first of all, an obvious observation, so this shows that due to the presence of this edge singularity, there are minimal configurations where, in some sense, the Young's law is violated, because here theta is larger than the Young's angle, due to the presence of this sharp edge. And by the way, this result provides an analytical validation of some heuristics provided in this physical paper by Oliver, Hu, and Mason. I think they also did some experiments to somehow confirm their heuristics. And the explanation of this angle is the following. Consider this theta prime angle here. So the angle formed now not with this part, but with the lateral boundary. So this is required that theta prime is equal to this angle. It is equivalent to require that theta prime equals the Young's angle with respect to this with respect to the oblique boundary, the oblique interface. How do we prove such a minimized result?
Sorry, can I ask? So this means that for the cylinder, you don't have this pinning.
Right.
For the cylinder?
You don't have this pinning.
No, you have it.
So when alpha is equal to 0, you don't have pinning effect.
No, you have it. Why not?
No, alpha is equal to 0,
That
yeah.
is bigger than pi over 2 minus 10. Why?
Pi over 2. Okay.
No, you have to so. Yeah, so, well, just a few words on how we prove this result by a calibration method. So, essentially, the idea is to construct a vector field in a neighborhood of, okay, this is a two-dimensional picture, but you have to think as a three-dimensional configuration. So this is the spherical cap, the blue one is the spherical cap. So the idea is to construct a vector field in a neighborhood of the spherical cap, this one. Such a vector field must be of constant divergence. It must coincide with the normal field on the boundary, on this part of the boundary of the spherical cap, plus this, and must satisfy also these inequalities here related to the wetting coefficients on this part of the boundary, so on this region here. So if you are able to construct a vector field satisfying all these conditions, then one can show that the spherical cap is a local minimizer with respect to perturbations that are contained in this neighborhood, and such that the wet region, also such that the symmetric difference of the wet between the wet region of the competitor and the original wet region must be contained in this red region here. So, for instance, this is an admissible competitor. And the idea how to construct these such vector fields is by foliations. So the basic principle in constructing this calibration is somehow to provide, to foliate a neighborhood of the spherical cap by a family of constant mean curvature surfaces, which will also be of, okay, it's more complicated than this, but this is more or less the rough idea. And once you have a defoliation, then you can take as a vector field the normal field to each of the to such a family of surfaces, of constant mean curvature surfaces. Well, here is an example of picture of how these foliations look like. Okay, now next. The last part of my talk, I want to say something about the regularity problem. Let me first recall a very classical result, going back to Jean Taylor result, which says something about the regularity in this situation. So not in our case, in this situation, if you have, so if the rigid support, the rigid solid, is regular enough, say of class C2, and you can also allow for a potential term, with bounded potential, and if E is a local minimizer of the capillarity energy in 3 dimensions, this result is true in 3 dimensions, and plus the potential term under volume constraint, then this part of the boundary of the minimizing configuration is a surface with boundary of class C1 alpha for all alpha between 0 and 1. Or in particular, the contact line is of class C1 alpha. This result has been then greatly generalized to the anisotropic case, by De Filippi's Maggi more recently in a paper of. They were also considering much more general energy functional here, so elliptic integrals in some sense. Okay, so in our case, what we want to understand is exactly the regularity of the drop in the situation where in the pinning regime, in the H pinning regime. So in the situation where the contact line has somehow reached the edge of the upper face of the nanowire. And so in particular, we want to understand whether the contact line touches the edge in a smooth way. Okay, an obvious observation is that our drop, in particular, it's a minimizer of the energy that I wrote before. In particular, it minimizes the capillarity energy. So we are assuming that the drop lies on the all above the plane of this upper face of the wire. Therefore, we can assume that such a configuration lies in the upper half space. So, in particular, this configuration minimizes the capillarity energy under a volume constraint among all configurations lying in the half space, such that the wetting part, the wetting region here, is contained in the upper facet of the wire. So this constraint is not really present in our original problem, but in particular, the energy, the configuration satisfies, is a minimizer with respect to this constraint. So we are adding artificially this constraint on the wet region. You may think of this as a sort of thin obstacle problem on the contact line. In some sense, we are saying that the contact line here must be contained in this region here above. Okay, and this is the result. So assume that E is a local minimizer for this problem here, and assume to start with that the section of the wire, so that is this little omega that we are using in this constraint problem. So the upper face of the wire is regular now, say of class C11. Then again we recover the usual result. Then once again the minimizer, the free boundary of the minimizer is a surface with boundary of class C1 gamma for all gamma between 0 and 1 alpha. So in particular, the contact line here is smooth up to the edge of the wire. Smooth is C1 gamma smooth. And well, here I'm writing an obvious fact that in the region where the contact line is away from the ridge, the Young's law is satisfied with equality, while when you reach the ridge, you have just an inequality. So in some sense, in this part of the contact line, the contact angle can be larger than the Young's angle. Okay, and this result follows, in fact, from an epsilon regularity result, which actually holds. So this is a full regularity result. So there's a full regularity result holds because we are in 3 dimensions. You cannot expect in no dimension as it is true always for minimal surfaces. But what is true in every dimension is an epsilon regularity result from which our result then follows. And the epsilon regularity result says the following, that consider a point here which lies on the contact line, lying on the so a point here, like here, on at the intersection of the contact line with the boundary with the edge of the wire. And assume that in a neighborhood of this point, say in this ball, the boundary is sufficiently flat, meaning that is contained in a strip, like this one, sufficiently small, and with the right slope, the slope given by the Young's angle. Okay, if the width of this strip is sufficiently small, then one can show that in the alpha ball, the boundary of E is in fact regular. It has the C1 gamma regularity that I stated before. So there's a sort of epsilon regularity result, which holds true in any dimension. And well, the proof is very technical, and but what are the main ingredients? The main ingredients are that we used is sort of an extension, a bounded extension of the so-called Savin spatial Harnack inequality, which allows us to implement a blow-up procedure to which we can linearize the problem and show that such a linearization leads to a sort of Signorini type problem. And so that in the end we can inherit the estimates that were already known for the Signorini problem. And in fact, the C1 gamma regularity for gamma up to 1 alpha is the optimal regularity for the Signorini problem. Finally, and this is the very last part, we wanted also to address the case where, as I said before, we were assuming that the section here, the section of the Y was C11. Now, what happens if we remove this assumption? For instance, we can consider polygonal sections, and in fact, these are observed, like in this picture. So there are Ys with polygonal sections. Okay, let me. This picture below here is taken from a paper, a PRL paper by Krugstrup and collaborators. This is in fact a simulation, and this is the situation where the drop has touched for the first time the ridge of the wire. So here the red points are the touching points. If you start from here and you grow a little bit more the drop, you start seeing that the contact line will start having a non-trivial intersection with the ridge. So these red lines are the intersections. You grow, the intersection increases, but as you can see from the pictures, the angles of the section are always dry. So the contact line seems to avoid always the corner. And so what we proved, in fact, this analytical rigorous proof of this fact. So now we are considering a polygonal section and a local minimizer in the sense of before, with the constraint that the wet region is contained here. And we proved essentially that also in this situation we get the same regularity of the drop. So the contact line is still a C1 alpha line, which in turn, this is the additional information, avoids the angles. So the contact line always cannot touch the angles. This comes from a sort of classification of the minimal cones for the problems, again through a blow-up procedure. So in some sense, what you observe is something of this type here, like in this picture. Okay, so thank you for your